స్కిన్ కేర్ రాలేదే. ఇక్కడ బాగా ఉంది. నో ఇష్యూ. ఇక్కడ రికార్డ్ అవుతుందా చూడు. అవుతుంది. ఇదే కదా. సిమిలారిటీస్. Close the door. Close the door. Okay, fine. Still anyone has to come? Still anyone has to come? Why? Adugu. Shall I start or anyone wants to come inside? Okay. Yeah. Let's start. So till last hours of class, we have discussed about the kinetics part. What exactly the kinetics? Which talks about the reaction rates, whether any reaction is going to influence with a maybe with the half lifetime or maybe with the temperature, what we call some activation energy, how the reaction rates are classified, homogeneous, heterogeneous. Fine. And then what are the different orders of the reactions? First order, zero order, second order, and how the reaction influence if it is a reversible or if it is irreversible, and what is a constant volume system, what is a variable volume system. That's what all we have discussed. So this all comes under the umbrella of the kinetics. So kinetics talks about the reaction rates. So in the early class itself, we have discussed what is a reaction rate, how it is a function of concentration, and what is called rate constant, which is again the function of temperature, which is described by the Arrhenius law. So that all have been covered. Now we are moving to chapter number 4, which talks about the reactor design. So from the chapter number 4, the things will be little bit complicated. Until and unless if you are good at your last 3 chapters, you can attempt the chapter 4 onwards. So you should be very familiar with the concepts till the chapter number 3 in order to move from chapter number 4, because chapter number 4 onwards we talk only about the design part. Till chapter number 3, the kinetics part, which we already discussed, we have done a lot of problems in the classroom itself. But chapter number 4 onwards, we need to design. What do you mean by design? We need to select a particular type of reactor, and also we need to design that particular type of the reactor. Design in the sense we need to find out the actual dimensions of the reactor. Let us suppose I took a batch reactor for time being. Now in the batch reactor, I have to design a batch reactor, means I need to give the dimensions of the batch reactor for my specified parameters of interest. That means, for example, for a reaction I took A gives rise B. For A gives rise B, I want certain conversion of B from A. That means I am fixing the conversion. I want 70% conversion in that batch reactor. Now to get 70% conversion in the batch reactor, what are the dimensions of my reactor? What is my length? What is my height? What is the type of stirrer we have used? What is the type of flow I have to maintain? Will I maintain some what we call a motor or a pump? So this all comes under the umbrella of the design. So that we discuss now from this class onwards. Okay. So what is chapter number 4, 5, 6, and 7? All four chapters, 4, 5, 6, 7 from the Levensfield textbook talks about the design part. How do we design the reactor? So before going to design part, first we should understand what are the reactors available. Maybe in instant of time in the previous class, I have just briefly given there are batch and there are flow reactors. A small classification I have given. So what is a batch reactor? A batch reactor is a one which is a container to hold the contents for a specific period of time. So there won't be any in, there won't be any out. Just it's a container, closed container. It's a closed container, just like a beaker which you took in the laboratory. You take a glass beaker, maybe 500 ml or 1 liter volume, and you add whatever the reagents or the ingredients, and then you left for the reaction to happen for 1 day, 1 hour, 1 year. That's called a batch. So a sort of a reactor wherein it's a closed one. There will not be any in, there will not be any out. Only one time we will keep it and we will leave it aside. That's called a batch reactor. It is different from the flow reactors. What is a flow reactor? There is a continuous flow of in as well as continuous flow of out. It's just like in our normal day-to-day pipeline systems. So when we open a tap in our household system, so there is a continuous flow of water. So in the type of flow reactors, there will be continuous flow of reactants in, continuous flow of reactants out. On the case, products we can out. Those called flow reactors. Now, again in the classification, we have different modes of interpreting the reactors. Let's look at one by one. We know this rate equation. What is the primary rate equation? Minus RA is equal to minus 1 by V dNA by dt. That is the first most formula that I told in the first class. 1 by V dNA by dt, where dN is number of moles. So dNA by dt into 1 by V is called minus RA. That is the rate of reaction we discussed, we defined. Okay. Now look at the design means what is the size and what is the type of reactor and what is the mode of operation. That's called design. We need to first look at the size, maybe small size, bigger size. What is the size? What is the type of the reactor? As I just now discussed, whether it's a batch type or a flow type. And then lastly, the method of operation. Is I operate intermittently or continuously? So all these three parameters comes under the design part. Look at this line. The conditions in the reactor vary with the position as well as time. What do you mean by this? See, when you took a beaker, when you took a beaker in your day-to-day laboratory, when you took a beaker, when you add some reactants, when you allow to react for some time, now imagine will the concentration, will the concentration same after 1 hour, same after 2 hours? The concentration, if I start the reaction after 1 hour, the concentrations will be same after 2 hours. That means what? Composition, concentration is going to vary with time. Vary with time. The conditions vary with time. Now look at the conditions vary with the position also. What do you mean by position? Let's take, if I took maybe in a small beaker you cannot understand. If I took any a sort of a bucket like system, a bigger rectangular type of system, where if I took sample at the left end, if I took sample at the right end, will the concentration at the left end will be same as concentration at the right end? If I took any reactor system, and in that reactor system, if I took the sample at the leftmost end, and if I took the sample at the rightmost end, will the composition same? The compositions will be same if it is a completely uniformly mixed. It is same if it's continuously uniformly mixed. Otherwise, it is not same. How it will be same? If it is not uniformly mixed. For example, usually what in mother do in the home, if you want to check the whether rice is cooked or not, what she do? Maybe after 15 or 20 minutes, she took only just one piece, and just it checks whether it nurtures or not, depending on the softness. She grants that yes, the rice was cooked well. How she does? She has not took either left hand or right hand or the center part of the rice. Just she took randomly, and then she nurtures it and checks yes, the softness is good, so rice was cooked well. How she does that? She presumes, or she assumes, or she guarantees that the contents are well mixed. The heat is transporting, giving heat in all directions such that entire rice was cooked well. So it is well uniformly mixed. If it is not well uniformly mixed, let us assume, what will happen? The rice, if I took from the left hand, maybe sometimes very hard. If the rice I took at the central part, because central part only the much of the heat will come from the burner. So the rice which is nearer to the center part will cook nicely, whereas rice at the either right hand or side or top and side will not cook nicely. So suddenly, if the mother takes the cook rice from the left part or right part, she assumes it was not cooked well. Getting or not? So the same way in the reactor also, if the contents are uniformly mixed, if the contents are well distributed, uniformly mixed, then the composition will be same. If the contents are not uniformly mixed, what will happen? If the contents are not uniformly mixed, what will happen? The compositions will vary with the position. From the left hand, the concentration is different. From the right hand, concentration different. From maybe 2 meters top, the concentration will be different. 2 meters down, the concentration will be different. Is it okay or not? So that's true. Even you can try in the home. Like everyone had a gas stove. But if you are not gas stoves, go back to the ancient times. People used to cook with the wood. Fine. So when we cook with the wood, there will not be heat uniformly to the container. ఏమవుతుంది అక్కడక్కడ రైస్ ముద్దలా ఉండిపోతుంది. ఈ ముద్ద ఇటు పక్క లేదా అటు పక్క క్రంచెస్ లా ఫామ్ అవుతుంది. అబ్జర్వ్ చేస్తే రైస్ ఒక దగ్గర బాగానే ఉంటుంది, ఒక దగ్గర ఏమో ముద్ద అయిపోతుంది. దట్ మీన్స్ వాట్? హియర్ ద కంపోజిషన్ ఈస్ డిఫరెంట్ ఫ్రమ్ ది అదర్ ఎండ్. మిగతా పార్ట్లో రైస్ బాగానే ఉంటుంది, కంపోజిషన్ యూనిఫామ్ ఉంటుంది. ఇక్కడ మాత్రం కంపోజిషన్ డిఫరెంట్గా ఉంటుంది. So that is what meaning of the conditions in the reactor vary with position. So when it will vary with position? When it will vary with position? If they are not well mixed, if they are not uniformly mixed. Clear? If it is uniformly mixed, well mixed, then composition is same throughout. If the contents are not well mixed, then they vary with position. Or I can say geometry. Position means geometry. అంతే కదా. సో ఈ ట్యాంక్లో ఇంత ట్యాంక్ తీసుకున్నాను, ఇంత ట్యాంక్లో ఖచ్చితంగా సేమ్ ఉండట్లేదు. అంటే ఏంటి? ఈ హైట్లో మారిపోతుంది లేదా ఇంకో హైట్లో మారిపోతుంది, అంటే జామెట్రీ మారిపోతే మారిపోతుంది. ఓకే. అండ్ సమ్టైమ్స్ టెంపరేచర్ అండ్ కంపోజిషన్, those two important very factors in all the reactor designs. Okay, fine. So again, temperature and composition vary from point to point within the reactor. Are you agree for that? Temperature and composition vary from point to point. Temperature in a reactor vary from point to point. ఎందుకు మారిపోతుంది టెంపరేచర్? Best example, when you took a rod and you want to heat the rod, మీరు ఒక రాడ్ తీసుకొని ఎర్రగా పొయ్యిలో పెట్టండి. The extreme left hand part where you kept in the heating zone will be of high temperature compared to the zone which you hold it. Temperature is same or different? Temperature is different. So in the reactor also, if you maintain uniform temperature, then only the temperature will be same throughout. Otherwise, temperature will definitely vary from point to point. ఇక్కడ ఈ ఎండ్లో ఉన్న టెంపరేచర్ ఆ ఎండ్లో ఉండాల్సిన అవసరం లేదు. అందుకోసం ఏం చేస్తాము, యూనిఫామ్గా హీటింగ్ కావాలంటే ఏం చేస్తాం మనము ల్యాబ్లో చూడండి, రౌండ్ బాటమ్ ఫ్లాస్క్ పెడతాము. సో దట్ హీట్ విల్ బి డిస్ట్రిబ్యూటెడ్ యూనిఫామ్లీ. మీరు ఫ్లాట్ పెట్టారనుకోండి యూనిఫామ్గా హీట్ రాదు, టెంపరేచర్ సేమ్ ఉండదు. ఈ పాయింట్ ద టెంపరేచర్ వేరే ఉంటుంది, ఆ పాయింట్ వేరే ఉంటుంది. సో యూనిఫామ్గా హీట్ ఇవ్వాలి అంటే మనం రౌండ్ బాటమ్ ఫ్లాస్క్ పెట్టుకోవాలి. మీరు అబ్జర్వ్ చేస్తే మోస్ట్ ఆఫ్ ద టైమ్స్ వీ హ్యావ్ ఓన్లీ రౌండ్ బాటమ్ ఫ్లాస్క్ ఫర్ హీటింగ్ జోన్. So that heat will be distributed throughout the reactor, so that the temperature will be same at every point. Otherwise, temperature will be different. Almost like a composition. Fine. So when we are designing, we need to take all these points into account. ఏమేం పాయింట్స్ అకౌంట్ తీసుకొని డిజైన్ చేసినప్పుడు రియాక్టర్ని, సైజు చాలా ఇంపార్టెంట్. ఒక రియాక్టర్ని డిజైన్ చేయాలంటే ఏ సైజు ఎంతలా డిజైన్ చేయాలనేది చాలా ఇంపార్టెంట్. సైజ్ ప్లేస్ మేజర్ రోల్. Size and then type of the reactor, batch plug flow reactor, CSTR, ఏ మోడ్లో ఆపరేట్ చేస్తున్నాం, బ్యాచ్ మోడ్లో ఆపరేట్ చేస్తున్నామా లేకపోతే ఇంటర్మీడియట్గా ఆపరేట్ చేస్తున్నామా సెమీ బ్యాచ్లో ఆపరేట్ చేస్తున్నామా, ఇవి చూసుకోవాలి. దీంతో పాటు ఏం చూసుకోవాలి, వీ నీడ్ టు లుక్ ఎట్ ద టెంపరేచర్ బికాస్ టెంపరేచర్ ప్లేస్ ఎ ప్రామినెంట్ రోల్. సో వెన్ యూఆర్ డిజైనింగ్ ఆల్ దీస్ థింగ్స్, దిస్ హ్యాస్ టు బి అకౌంట్ ఇన్ ద మైండ్. ఓకే. Now look at the batch reactor. We already discussed it, but let me go through in glance so that we'll go through the next part of the slides. See, batch reactor is a very simple reactor which you already seen in the usual laboratory says. Fine. It needs very little supporting equipment, is it not? So everyone can catch hold of the batch reactor because we are doing we start with the first basic lab of chemical engineering, either with the chemical technology. We start with small beakers. So very small supporting equipment, ideal in the sense and industrially used when small materials are to be handled. When we want very small amounts, we usually choose the batch. Okay. Look at the next flow reactor is called steady state flow reactors. Steady state flow reactors. When we want large quantities, we need to rely on the flow reactors. చిన్న చిన్నవి అనుకోండి బ్యాచ్ రియాక్టర్కి వెళ్ళిపోవచ్చు. పెద్దవి అనుకోండి when we want large quantities, we need to look at the flow reactors. Okay. The first and foremost flow reactor is plug flow reactor. Plug flow reactor. Okay. Now what is the importance of this plug flow reactor? The rate of reaction is fairly high. Ultimately what we require, the rate of reaction only, is it not? So when we want rate of reaction to be high, choose plug flow reactor. So plug flow reactor rate of reaction is extremely high, fine, and very good product quality. If you operate in the plug flow reactor, the product quality is good, fine. So where we use, usually they are used in all oil industries, all petrochemical industries, fine. The next one is semi batch. Semi batch, not batch, semi batch. What is batch? What is batch? Go back to batch slide. I already told batch. There will not be any, there will not be any. One time only we will keep it and keep it aside. Batch. But what is semi batch? It's a batch only. That means closed one, leave left for some more time to execute the reaction. But it is semi. That means sometimes there may be only one inflow, or sometimes maybe one outflow, or sometimes maybe in and out, but asked to stay for longer times. It's called semi batch. You look at the figure. Semi batch. See in this figure, there is one inflow given, but just one inflow is giving and asked to stay for longer times. So volume and composition changes. Here, volume and composition is unchanged because I am keeping all the time A and B pouring and asked to react. So my volume and composition is unchanged. Last one inflow and one outflow. but asked to react for some time. It's all called semi-batch reactions. We are not bothered about semi-batch. We are mainly focused on batch, plug flow, and mixed reactor that we will discuss. So semi-batch is not important for us. Fine. So usually, what is the material balance we adopt for designing is either we do mass balance, or we do energy balance, or we do component balance. When we are designing means we need to balance. It's just like usually in mother or in any house industry we do like that. What is inflow, what is my expenses, and what I want to save. So I do the balance. So the material balance, maybe sometimes what is the reactant is entering, what is leaving, and any product formed inside or any accumulation happens. Let us look at the equation. Yes, look at the equation. See, rate of reactant flow into volume is equal to rate of reactant flow out plus rate of reaction loss plus rate of accumulation. It's a fundamental material balance equation. How do we remember this equation? Very simple. See, if I took a reactor, if I took a reactor, let us say I'm sending some reactant into the liquid, into the reactor. If I am sending, so what I am sending should be equal to rate of reactant flow into should be equal to what are the changes in the reactor. If I said something, let us say A gives rise B reaction. That means what? I'm sending reactant A to the reactor. What will happen if I send to the reactor? Tell me what will happen if I send to the reactor. Slowly A will convert into B. Slowly A will convert into B. Fine. A will convert into B. That means what? A is disappearing in the reactor. Fine. So that is called this rate of reactant loss. That will happen in the reactor. When I fed A will definitely disappear. A will loss. That is called rate of loss. And tell me whether all A which I send to the reactor will react to form B. Definitely, sometimes some of the reactant A will be as it is left without pairing to form B. That happens. 60 మంది వస్తారు లోపలికి అందరూ 60 మంది ఒకేసారి డిగ్రీ తీసుకుని పోతారా? ఖచ్చితంగా ఒకరిద్దరికి బ్యాక్లాగ్స్ ఉంటాయి. Because they are not unable to clear within the stipulated time of 4 years. Similarly, which I send A reactant into the reactor, sometimes there will be some part of A which is unreacted. Will as it is be in the reactor. That's called accumulation. Accumulating in the reactor, unchanging, not forming B. So that is called rate of accumulation, rate of disappearance. But definitely there will be some out of the reactor after reacting. That's called out. So in is equal to out plus accumulation plus rate of disappearance. In is equal to flow in, flow out plus disappearance plus accumulation. It's a standard format and we need to remember. So if I do energy balance, let us suppose ఏం వాడతా ఎనర్జీ బ్యాలెన్స్ లో ఈ టర్మ్స్ ఏమే రేట్ ఆఫ్ ఫ్లో ఇన్ బదులు ఎనర్జీ ఇన్ ఆర్ హీట్ ఇన్ ఈజ్ ఈక్వల్ టు రేట్ ఆఫ్ హీట్ అవుట్ ప్లస్ రేట్ ఆఫ్ హీట్ డిసిపేషన్ ప్లస్ రేట్ ఆఫ్ హీట్ అక్యుములేషన్. ఇన్ ఈజ్ ఈక్వల్ టు అవుట్ ప్లస్ disappearance plus accumulation. So this is a mass balance equation. Sometimes we may use energy balance equation. Sometimes we use component balance equation. What is component balance? Component. Let us say I'm talking about only reactant A. So I will write rate of reactant A into system is equal to rate of reactant A out of the system plus rate of disappearance of A plus rate of accumulation of A. ఏ కాంపనెంట్ కాదు బి అన్నారు అనుకో బి మార్చుకోండి, సి అన్నారు అనుకో సి మార్చుకోండి. దట్స్ కాల్డ్ కాంపనెంట్ బ్యాలెన్స్. మాస్ బ్యాలెన్స్, ఎనర్జీ బ్యాలెన్స్, కాంపనెంట్ బ్యాలెన్స్. Format is the same. When you are writing this format of balancing, make sure that units are consistent. Make sure that units are consistent. What is units? Whatever you write here in some rate and రాస్తున్నాం. Rate కి ఏ యూనిట్స్ ఉంటాయి? రేట్ ఈజ్ ఈక్వల్ 1 బై వి డిఎన్ఏ బై డిటి అనుకున్నాం. అంటే ఏంటి? మోల్స్ పర్ సెకండ్ పర్ యూనిట్ వాల్యూమ్. ఓకే, సో లెఫ్ట్ హ్యాండ్ సైడ్ ఏ యూనిట్స్ ఉంటాయో రైట్ హ్యాండ్ సైడ్ అదే యూనిట్స్ మెయింటైన్ చేయాలి. యూనిట్స్ షుడ్ బి కన్సిస్టెంట్. క్లియర్? Energy balance already told. So you can go through these things because I kept for your reference only. Now there are some new terms when the design part comes into the picture. What are the new terms? We already know. Yeah, we already know the concentration term. This we know. What is C naught? We know concentration term. Now there are two new terms came here. See, look at here. FA naught, nu naught. This is not V, new. So nu naught and FA naught. What is this FA naught and nu naught? The two new terms comes into the design part is FA naught is molar feed rate. Molar feed rate. Units of moles fed per hour. That's called molar feed rate. And nu naught is volumetric flow rate. Volumetric flow rate, that is volume units per time. So if you look at the units here, volumetric flow rate, meter cube per hour, moles per hour. So the two new terms will come along with the other terms. You know already other terms like what is called concentration, conversion, symbols you know. So let's not worry about all these things. Let's go back to the our usual context, single reactions. Let us look at the derivation part of the performance equation. See, chapter number 4 is nothing. Chapter number 4 is a basic introduction to the chapter number 5. Chapter number 5 is very important because lot of varieties on the chapter number 5. To introduce chapter number 5, chapter number 4 has been decided. To introduce some of the terms, introduce some of the context only, chapter number 4 has come into picture. Okay. Now let us come to the chapter number 5 where we are deriving the performance equations. Let us look at for the isothermal case. What is isothermal case? So in chapter number 5, we will first look at all the derivations part or design part for the constant temperature case. Chapter number 8 will be on non-isothermal. That means when temperature is varying, how do we design? So chapter number 5 and 6 are all for the constant temperature case, isothermal. Okay. Now look at the batch reactor. Batch reactor is why it is unsteady state. What is steady state? So we should be clear in context of steady state and steady state. Steady state means does not vary with time is called steady state. That means the time when I look at composition will be same as the time when I look at after 1 year. Steady state means that is not varying with the time is called steady state. Steady గా నిలబడమని ఎందుకు చెప్తారు? అలా నిలబడితే అలాగే ఉండాలి, కదలకూడదు, మెదలకూడదు. అంటే ఏంటి? టైం ఎంత పెంచినా నేను 10 నిమిషాలు చూసినా అలాగే ఉంటున్నానంటే అర్థం ఏంటి? టైంతో వేరీ అవ్వట్లేదు వాడు. It's called steady state. Steady state, the state where it is in steady means the parameters are not varying with the time. But whereas batch is unsteady state. Why? Because I told you when I took a batch reactor, so the instant if I pour, if I give some half an hour time, The concentration is changing after half an hour. After half an hour, time is varying. Concentration is same? No, because A I fed, the concentration of A initially may be 10 moles, but after half an hour, it will not be 10 moles. It will be decreased, maybe 4 or 5 moles, because A is converting it to B. So the concentrations are changing. So the reactor is called unsteady state reactor, but it is well mixed. So what do you mean by well mixed?
Uniformly mixed.
What do you mean by well mixed?
Uniformly mixed.
Yes, composition is same throughout the reactor. That means there is no change with respect to the geometry. If I took sample here, will be same. If I took sample here, will be same in in a reactor. If I took from the left end or the right end or the central part or the topmost, everything is well mixed. Remember these points. A batch reactor is a well mixed reactor, but it is unsteady state. Keep these points very important. It's well mixed. So it is not varying with the geometry, not varying with the reactor size, but it is varying with the time because it's unsteady state. Clear? But at any instant, the composition is throughout the reactor is uniform. What do you mean by this last line? At any instant, the composition is uniform throughout the reactor. Let us say, for example, if I took maybe after half an hour, I took the sample here, I took the sample here, I took the sample here. Will it same? That's what it's saying. At any instant, the composition is throughout the same because it's well mixed. That's what I'm meaning. Well mixed means it will not change. Even if I took here, even if I took here, even if I took here, it will not change. But it will change after half an hour. Maybe after first 1 hour I took here, maybe 10 moles. But if I took after 1 hour, it will not be 10 moles. It may be 20, 20, 20. All the points it will be 20 only because they're well mixed. Clear? Now plug flow reactor. Plug flow. There are different names for the plug flow. Plug flow is also called slug flow or piston flow or ideal tubular or unmixed. There are all names for the plug flow reactor. But it is a steady state flow reactor. What do you mean by steady state?
No change.
We are talking about ideal cases. We are talking about ideal cases. Now, what exactly this plug flow reactor? There may be lateral mixing of the fluid. See, it will be always look in this fashion. Plug flow reactor. Plug flow reactor. It's like almost a pipe, like a tubular type, where you send the feed continuously in and take the feed continuously out. The product. Now, what is this lateral mixing? See, when I send the fluid here, you look at the direction of the fluid. When I send the fluid here, this is called axial direction. Because if it is a tube, the direction which I send the fluid is called axial direction. And perpendicular direction is called lateral direction. So what they are saying is for the plug flow reactor, there will be lateral mixing. That means along the direction of the axial, there will not be any mixing. Only in the lateral direction. That means the fluid first top layer will be mixing with the fluid next top layer. So the lateral mixing is there, but not axial mixing. And now, why it is called? There will not be any overtaking or mixing with any other element. In the plug flow reactor, there will not be any overtaking. What do you mean by this overtaking? Let us say, see, for example, I have sent here some fluid here. From here. This is the first left end. Now, let us say if one fluid particle is here and it will always go in this direction only. It will not come back. When I fed here, it tries to go in the same direction with whatever velocity I kept. That means what? It will not react with the back flow. It will not come off or it will not react with the back particle. That's called mixing with any other element. There will not be any mixing. There will not be any overtaking. See the fluid if I send here, it will not overflow. It will not overtake to move front. Those things will not happen. Okay. So no mixing or diffusion along the path, along the flow. No mixing or diffusion along the axial direction. Now let us look at the CSTR. It is also called a back mix reactor, mixed reactor, continuous flow stirred tank reactor, constant flow and also constant, what do you call, the flow tank reactor. So the different names for this reactor is called, see, constant flow stirred tank reactor. Actually, we usually call it a CSTR, but that is wrong. We always call it a CFSTR. Either continuous flow or constant flow stirred tank reactor is called CFSTR. It's also called back mix reactor. You see, look at the reactor here. See, this is a type of a CSTR where I am feeding the feed in and out. Look at here, if I fed the liquid here or the reactant here, I am giving the stirring option. That means mixing is there, well mixed case. But see, look at here, some fluid particle here will maybe left here or maybe come over here or maybe left here, maybe here, or same fluid may be going back up. See the directions. Or sometimes what will happen, when a movement if I fed here, some of the liquid particles directly go back and come out, called overtaking. Actually, what is the meaning? This particle should be come down, stir properly, get the product, come out. But sometimes what will happen? Sometimes the liquid will directly bypass here, come out. Overtaking call. Or back mixing. What is back mixing? The moment the particle comes here, it stills here only, but again it is going back. These are not possible in plug flow. That's what I told you in the previous class. In the plug flow, there won't be any back mixing, there won't be any overtaking. These are only possible for the CSTR. But say well mixed case. Okay, fine. So the names are, look at the names, back mix, or mixed, or CSTR, or CFSTR, all means same. Fine. Okay. Now look at the volume, which we already know what is VR, what is V. We discussed it. The volume of the reactor is different from the volume of the fluid. I told you. Fine. Now how do we derive the equation for batch reactor? So I told you the batch reactor, what is the equation? I told you what is in, what is out, what is disappearance, what is accumulation. For the batch reactor, I already told there is no in, there is no out, because it's a closed container. Take the reactants, keep it aside. So the in and out will be zero. So we've been left with only two terms: disappearance, accumulation. So disappearance is equal to minus of accumulation. So how do you write disappearance? From the rate expression, we know minus R is equal to 1 by V dNA by dt. So if I write in terms of units as moles per time, all units in the moles per time, minus R into V will be my disappearance. And what is my accumulation? dNA by dt. dNA by dt, if I write in terms of conversions, Na is equal to Na naught into 1 minus Xa, you know that. So we will get minus n naught into dx by dt. Okay. So ultimately minus RA into V is equal to Na naught into dx by dt. So this is the batch reactor performance equation. Minus RA into V is equal to Na naught into dx by dt. If I just rearrange it, integrate it, get T, I'll get Na naught in integration of 0 to xa dx by minus R into V. So what is the performance equation for a batch reactor? How do we derive? Very simple. Take the material balance equation. In is 0, out is 0. Only two terms, disappearance, accumulation. Disappearance is minus RA into V. We know that. Accumulation is dNA by dt. So Na is equal to Na into 1 minus xa. So dNA by dt is it. Take the derivative. You'll end up with minus RA into V is equal to Na naught into dx by dt. Or if I integrate it, I'll get T is equal to Na naught integration of 0 to xa dx by minus R into V. If I took for the constant volume case, what is constant volume case? Constant volume or constant density case where epsilon A will not be there. Constant volume. So I can took V out. And A naught by V is C A naught. So the equation will become like that. And A naught by V is C A naught. Because constant volume case I am talking about. If it is a variable volume, I need to incorporate this expression. I already told. V is equal to V naught into 1 plus epsilon A xa. V in place of V, replace V naught into 1 plus epsilon A xa. So if you know the first expression for a batch reactor, minus RA into V is equal to Na naught into dxa by dt. If I know this batch reactor performance equation, everything you can derive. Now the most important part comes now. Look at the case. Look at the expression. You remember what is the expression? If you look at the expression, see, P is equal to Na naught integration of 0 to xa dxa by minus RAB. Remember the expression for a batch reactor. For batch reactor, from this equation of integration, you will end up with this. So P is equal to Na naught 0 to xa dxa by minus RAB. If I draw 1 by minus RA, if I draw 1 by minus RA versus this xa, if I draw a plot minus RA minus 1 by RA versus xa, I'll get, and the integration, because the integration minus 1 by RA V, if I do the integration, if I take back that P N A naught V, I'll get area is equal to P by N A naught. Because what is the meaning of integration? What is the meaning of integration? Area. Area. Area under the curve is called the integration part. So the area under this curve, the area under this curve is P by N A naught. So if I plot minus 1 by RA V 2xa, the integration will end up with area called P by N A naught. General case. If I took for constant density, that V comes out, Na naught by V will become Ca naught. So expression will be this one. So if I plot minus 1 by RA versus Ca, xa if I draw, I'll get T by Ca naught. In terms of Ca naught, if I draw minus 1 by versus Ca naught, I'll get area equal to P. So ultimately, batch reactor equation, what is the equation? And what I will get if I plot? If you look at the plots, if I draw minus 1 by RAB versus XA, I will get T by NA naught, the area under the curve. Because the problems will come like this only. They will give data of rate versus the conversion. So you have to draw minus R 1 by RAB 2XA, get a curve, find out this area, you will get T by NA naught. From that you will get T. So they will ask the what is the time for the particular conversion. That is a batch reactor. I want 50% conversion. So 0 to 50. So this much area you need to calculate. And accordingly that is T by N naught. Multiply the N naught you will get T. Fine. Let us look at the two important parameters for the flow reactor's definition. Space time, space velocity. Space time is called tau, different from T. T different. This is T is a normal time that we use for the batch reactor. But when we comes to the flow reactors, what are the flow reactors? Maybe CSTR or a plug flow. There is only two flow reactors. Because in CSTR there is a continuous in, continuous out. In a plug flow there is a continuous in, continuous out. So only two flow reactors we have, either CSTR or plug flow. For the two reactors we have two terms. Space time, space velocity. Space time is called tau. Space velocity is called S, which is inverse of tau. So look at the definition. Time required to process one reactor volume at specified conditions. The number of reactor volumes at specified condition can be set in unit time. Two very simple definitions, and the meaning is also very same. Let us say, for example, 5-hour inverse space velocity. See, space velocity, 5-hour inverse. What is the meaning of space velocity? Number of reactor volumes. That means 5 reactor volumes has processed in 1 hour time. That's called 5-hour inverse. Let's say 2 minutes of space time. What do you mean by 2 minutes? One reactor volume feed at specified conditions can be done in 2 minutes. So batch reactor there will be small t, but for the flow reactors you have to use tau, space time, space time. So the characteristics of time in the flow reactor is space time tau. Okay. So what is the formula for tau? Tau is equal to V by VA naught. What is V? Volume. What is V naught? Already told, volumetric flow rate. Okay. But we know FA naught is equal to nu naught CA naught. What is FA naught? Molar feed rate. I told molar feed rate. Molar feed rate is equal to volumetric flow rate multiplied by the concentration term. FA naught is equal to nu naught into CA naught. Now I am replacing this nu naught as FA naught by CA naught. So FA naught by CA naught. So the expression for tau will become CA naught V by FA naught. What is FA naught? Molar feed rate. Units is moles per time. That is equal to volumetric flow, that is meter cube per time, into concentration, moles per meter cube. So meter cube it cancels, you will get moles per time. That's called FA naught. Look at the derivation of the steady state mixed flow reactor. CSTR. See, in CSTR, already well mixed is a big condition and steady state. Well mixed. Well mixed. What do you mean by well mixed? That means whatever inside will be same as concentration out, not changing. అంతే కదా. Go back to the CSTR figure. Yes. You see, CSTR figure. The composition is well mixed means if I took concentration here, or here, or here, or here, all the same constant, same. Because it's well mixed. Nothing will change. So the concentration or composition inside the reactor will be same as out. Fine? Well mixed. When it is well mixed, will you see any accumulation? That's why what we do, usually mother will try to take something called garita and try to stir it, try to mix it. When you are giving uniform mixing, there will not be any accumulation. When accumulation will come? When accumulation will come? When will the heat crunches of rice will come? If there is no proper mixing, if there is no proper heating. If uniformly mixed means whatever the composition I took will be uniformly throughout the reactor will be the same. So where is the part of accumulation comes here? A will completely convert. There will not be any left of unreacted A because they are uniformly mixed. If I go back, maybe here itself. If I take here, if I take here, when I fetting component A, there will not be any place where A is unreacted. ఎక్కడ అన్రియాక్టెడ్ కేసే దొరకదు మీకు ఎందుకంటే కంటిన్యూస్గా మిక్స్ చేస్తున్నాము యూనిఫామ్గా వెల్ మిక్స్డ్ కండిషన్ అంటున్నాం ద అజంప్షన్ ఐ టుక్ ఈజ్ వెల్ మిక్స్డ్ ద అజంప్షన్ ఐ టుక్ ఈజ్ వెల్ మిక్స్డ్ సో దట్ మీన్స్ there is no part in the reactor where unreacted A is left. ఏ రియాక్ట్ కాకుండా ఎక్కడైనా మిగిలిపోయిందనే కాన్సెప్టే లేదు ఎందుకంటే యూనిఫామ్గా మిక్స్ చేస్తూనే ఉన్నా రియాక్టర్లో అంటే అర్థమైంది అక్యుములేషన్ ఉంటుందా సో ద అక్యుములేషన్ విల్ బి జీరో సో ఇన్ ద మాస్ బ్యాలెన్స్ ఈక్వేషన్ ఫర్ CSTR the accumulation will be zero because well mixed. Now I took the material balance. I use flow rates, molar flow rates. So Fa naught is the in. Let us see the figure. You see the figure? I am feeding with concentration initially Ca naught. Initial there is won't be any conversion. So X naught is zero. Flow rate, volumetric flow rate is nu naught. And with initial molar feed rate Fa naught. And there is a stirrer, there is a reaction, and there is an out. Out will be final concentration CAF, conversion XAF, and FA, molar feed rate of A out. So in, out, only disappearance because accumulation is zero. I already know FA is equal to FA naught into 1 minus XA because NA is equal to NA naught into 1 minus XA or CA is equal to C naught into 1 minus XA. We know the formula. So FA naught is in, FA is out. But I write FA is equal to FA naught into 1 minus XA. So if I substitute and if I remove, I will end up with an equation. If I substitute, the disappearance is minus RAV, fine. Accumulation is zero, and end up with it. So the performance equation for CSTR is V by FA naught is equal to tau by CA naught is equal to XA by minus RA. V by FA naught is equal to tau by CA naught is equal to XA by minus RA. That is the final performance equation for CSTR. Okay. Now look at the plots. So V by F naught is equal to tau by C naught is equal to XA by minus RA. That means if I plot minus 1 by RA versus XA, minus 1 by RA versus XA, I am getting V by F naught area because the area is this part. The area is V by F naught or tau by C naught. Now you should ask a question here. In earlier batch reactor, we took area till this part only. Why I am taking now complete area? There is no integration here. For batch reactor, there is an integration term. Here there is no integration. Just V by F naught is equal to tau by C naught is equal to X A minus RA. So I need to take complete area. Now this complete area is called V by F naught. If I took for the constant density system, so we can become now, it will become Ca naught in terms of, so if I draw minus 1 by Ra versus Ca, I'll get area called tau. Okay, so the plots are very, very, very important. For CSTR, if the problem comes, we need to plot minus 1 by RA versus XA. And the area of the plot is called V by F naught. From V by F naught, either we can calculate V, that is volume of the reactor, because that is an important question. How do you size the reactor means we need to find V. How to find V? We need to first draw a plot. From the plot, the area, find out the area, you get V by F naught. Multiply F naught, you will get V. For example, in the same CSTR, if in terms of concentration is given, you need to draw minus 1 by RA versus concentration and find the area. That area is tau. Tau is nothing but V into C naught by F naught, already told, because tau is V by V naught. Nu naught, how I replace, because F naught is equal to nu naught into C naught. Okay. So look at plug flow reactor. Maybe for this expression where minus RA is involved, wherever, you can derive for the first order, second order by replacing. You look at here for the first order, constant density system first order. The expression will become k tau is equal to x by minus 1 by 1 by. See, these are all small derivations only. Nothing much what we call learned mathematics. Very simple. In one step you will get it. Only thing is properly we should use the brain. What is minus RA? Just minus RA is equal to k into CA power 1 first order. Go back to the equation here. I should keep here minus RA as k into CA. And k into CA, you multiply k here, k tau. Is it not the expression that we got? Look at the expression. Just k tau. Simplification. Replace XA. What is XA? I already told CA is equal to CA naught into 1 minus XA. Or XA is equal to 1 minus CA by CA naught. Replace this XA by 1 minus CA by CA naught. You will get this expression. Very, very small fundamental derivations. Maybe in 1 or 2 steps you will get it. But it is always better to remember the formulas in terms of examination. Because in examination we have been time bound. You cannot go and I want to derive there itself. Gone. All 3 hours will be in derivation only. You can't solve any problem. So we need to sometimes remember the fundamental formulas. For CSTR, the performance equation is V by Fa naught is equal to tau by C naught is equal to XA by minus RA. That's all. If I know the fundamental equation, I can derive because I know what to substitute minus RA. What to substitute variable volume, I will substitute V is equal to V naught into 1 plus epsilon A XA. That part I can do, but fundamental equation you should to have in your mind. So this is the equation for first order constant in CSTR. Similarly, maybe for the first order expression for variable volume. That means you've been replacing V as V naught by 1 plus epsilon X. The next most important is the plug flow reactor. The two assumptions are steady state, no axial mixing. I already told there will not be any axial mixing. And you see, there is no well mixed condition here. సో వెల్ మిక్స్డ్ లేదంటే అర్థం ఏంటి చెప్పండి ప్లగ్ ఫ్లోలో వెల్ మిక్స్డ్ అనే అజంప్షన్ లేదు అంటే అర్థం ఏంటి చెప్పండి కంపోజిషన్ ఇస్ వేరింగ్ విత్ యువర్ జామెట్రీ ఇస్ ఇట్ నాట్ కంపోజిషన్ ఇస్ వేరింగ్ విత్ యువర్ జామెట్రీ ఇస్ ఇట్ నాట్ చూడండి ఇప్పుడు నేను ఇక్కడ నుంచి ఫెట్ చేశాను ప్లగ్ ఫ్లోలో ఇక్కడ కంపోజిషన్ అంటే ఈ లెంత్ మేబీ లెంత్ 1 సెంటీమీటర్ తీసుకుంటే ఎల్ ఈక్వల్ టు 10 సెంటీమీటర్ తీసుకుంటే సేమ్ ఉంటుందా that means with the geometry composition is changing with the geometry starting first centimeter length లో కంపోజిషన్ ఒకలా ఉంటుంది ఇక్కడికి వచ్చేసరికి కంపోజిషన్ ఇంకోలా ఉంటుంది ఎందుకంటే by the time when it is going there will be lateral mixing composition is changing so well mixing అనే కండిషన్ లేదు చూడండి ఓన్లీ స్టడీ స్టేట్ కి వచ్చాం fine now you should ask a question why we are going for differential volume ఇందాక హోల్ రియాక్టర్ నేను బ్యాలెన్స్ చేశాను మీకు అబ్జర్వ్ చేశాను లేదో హోల్ రియాక్టర్ బ్యాలెన్స్ చేశాను ప్లగ్ ఫ్లో అది బ్యాచ్ కానీ సిస్టర్ కానీ ప్లగ్ ఫ్లోకి వచ్చేసరికి బ్యాలెన్స్ లో జీనికి వేస్తున్నాం ఒక రియాక్టర్ లో జీనికి వేస్తున్నాం ఈ ముక్కకి వేస్తున్నాం బ్యాలెన్స్ డిఫరెన్షియల్ వాల్యూమ్ తీసుకున్నాం because there is no well mixing condition composition is varying with geometry మారిపోతుంది కాబట్టి ఏం చేయాలి జామెట్రీ మారిపోతుంది కాబట్టి నేను ఒక చిన్న జామెట్రీ తీసుకున్నా చిన్న రియాక్టర్ వాల్యూమ్ I took small reactor volume of dv చిన్న dv అనే వాల్యూమ్ తీసుకున్నాను దానికి బ్యాలెన్స్ చేస్తున్నాను ఈక్వేషన్ లో So this question has asked several times in most of the interviews and no one is able to answer this question. In derivation of the plug flow, why you chosen the differential element volume? Why you have not chosen for the CSTR? What is the answer? మీరు ఇప్పుడు సిఎస్టీఆర్కి వెళ్ళండి సిఎస్టీఆర్ ఇగో ఇదే కదా సిఎస్టీఆర్ ఇదే చూడండి ఇదే కదా then as a whole reactor కి maybe the first equation yeah ఈ మాస్ బ్యాలెన్స్ ఈక్వేషన్ యాజ్ ఎ హోల్ రియాక్టర్ వేసాను ఎంత ఇన్ వెళ్తుంది ఎంత అవుట్ వస్తుంది చూడండి ఎస్ వాట్ ఈజ్ ఇన్ వాట్ ఈజ్ అవుట్ కంప్లీట్ రియాక్టర్ వేసాను నేను బ్యాలెన్స్ కానీ ప్లగ్ ఫ్లోకి వచ్చేసరికి ఐఎమ్ నాట్ యూజింగ్ కంప్లీట్ రియాక్టర్ ఎందుకు బికాస్ ఇట్స్ చేంజింగ్ విత్ యువర్ జామెట్రీ ఫైన్ కంపోజిషన్ ఈజ్ నాట్ సేమ్ యూనిఫామ్లీ ఇప్పుడు ఇక్కడ తీసుకున్న కంపోజిషన్ ఇక్కడ తీసుకున్న సేమ్ ఉన్నప్పుడు నేను రియాక్టర్ కంప్లీట్గా వేస్తే సరిపోతుంది కానీ ప్లగ్ ఫ్లోలో అలా కాదు ప్లగ్ ఫ్లోలో 1 సెంటీమీటర్ తీసుకుంటే కంపోజిషన్ 10 సెంటీమీటర్ తీసుకుంటే కంపోజిషన్ వేరీ అయిపోతుంది సో ఇట్ ఈస్ చేంజింగ్ విత్ యువర్ వాల్యూమ్ జామెట్రీ ఇట్ నాట్ వెల్ మిక్స్డ్ కండిషన్ అయితే కానే కాదు ప్లగ్ ఫ్లోలో So I need to take a small geometry, then under geometry I do balance, then I try to integrate it for the entire reactor. చిన్న జామెట్రీకి బ్యాలెన్స్ చేసి దానికి ఇంటిగ్రేషన్ చేసాం అనుకోండి, పెద్ద రియాక్టర్కి అంటే ఎంత వాల్యూమ్ కావాలంటే అంత సైజుకి నేను ఇంటిగ్రేషన్ చేస్తే నాకు వస్తుంది. ఓకే. ఎస్. సో So if I do balance, I'll end up with an equation. Let me go to the equation itself directly because small only you can understand because CSTR I defined. So you end up with an equation more similar to CSTR, but there's an integration term. V by F naught is equal to tau by C naught is equal to integral 0 to x a dx by minus r. For CSTR there is no integration. Remember CSTR equation? Go back. You see? V by F naught is equal to tau by C naught is equal to x a by minus r a. XA by minus R, there is no integration. But for the plug flow, you will get an integration. Now look at the graphs. So as I told, when integration comes, your area will be that part only, not entire part. సో చాలా మంది చేసే మిస్టేక్స్ ఇక్కడే. వాళ్ళ ఫార్ములా బాగానే గుర్తుపెట్టుకుంటారు, గ్రాఫ్ బాగానే గీస్తారు, ఏరియా దగ్గర తప్పులు చేస్తారు. ప్లగ్ ఫ్లోలో ఇంటిగ్రేషన్ టర్మ్ ఉంది అంటే ఏరియా కర్వ్ ఎంతవరకు ఉందో అంతవరకు ఏరియా కట్టాలి, అంటే ఈ పార్ట్ నేనే కట్టాలి ప్లగ్ ఫ్లో. అదే సిఎస్టర్కి అయితే ఇంటిగ్రేషన్ లేదు, మొత్తం ఏరియా కట్టాలి. మళ్ళీ సేమే -1/RA అవతల పక్క వేయాలి, కింద ఎక్స్ఏ వేసుకోవాలి, అవన్నీ మామూలు. ఇంకొకటి చాలా మంది ఏరియా కట్టడం కూడా తప్పులు చేస్తారు. ఇప్పుడు గ్రాఫ్ ఏరియా ఎలా కడతారు మీరు? హౌ డు క్యాలిక్యులేట్ ఏరియా? We try to take the length. ఇప్పుడు ఈ ఎక్స్ యాక్సిస్ ఎంత పెట్టుకున్నాము యూనిట్, ఈ వై యాక్సిస్ ఎంత పెట్టుకున్నాము, ఎన్ని బాక్స్లు వచ్చాయి, ఒక్కొక్క బాక్స్ వాల్యూ ఎంత. ఫర్ ఎగ్జాంపుల్ ఇక్కడ ఒక బాక్స్, ఇక్కడ ఇది 1 సెంటీమీటర్, ఇది 1 సెంటీమీటర్ పెట్టుకున్నాము. 1 into 1 ఈజ్ మై ఏరియా ఆఫ్ 1 బాక్స్. అలాంటి బాక్స్ ఎన్ని ఉన్నాయి క్యాలిక్యులేట్ చేసుకుంటాం. దట్ ఈస్ వన్ వే. దట్స్ అ క్రూడ్ అప్రాక్సిమేషన్. బట్ ఎగ్జాక్ట్ గా కావాలంటే ఎలాగా? మర్చిపోయారు. Go by your trapezoidal rule, Simpson's rule. Area under the curve. Simpson's 1/3 formula, 3/8 formula, Chip-Troil formula. So you'll get accurate estimation of the area under the curve. Okay. So same thing for zero order. Go back here, substitute here in this equation. What is the equation? V by F naught is equal to tau by C naught is equal to integral dx by minus RA. Replace minus RA by KCA1 first order or KCA power 0. That is only K here. And do integration. You'll end up with the equation. If it's a very volume, if it's a reversible reaction, see in CRE, more often in the end exam, they will ask the problems. But for any examiner, if he is interested not in problems, he will ask derivations. Simply first question. in a plug flow, derive the performance equation for zero order reaction. That means you have to end up here. So for first of all, I should know what is the performance equation for plug flow. V by F A naught is equal to tau base A naught is equal to integral 0 to XA dXA by minus RA. Then if I know that equation, I replace minus RA is equal to K into CA power 0. And then I do some integration, I'll end up with the equation. That's all. So either derivations or the problems, but there is no theory. So you should understand the concepts. Then only you will comfortably attempt in the end exam. Clear? So from the next class onwards, we do the problems. So bring the graph sheets. We do all sorts of problems from the batch, CSTR, and plug flow. So this is still chapter 5, the derivations. And you can do these derivations very simple. I don't want to trouble you in deriving the class. If you do problems in the class, that will be give more conceptual knowledge. ప్రాబ్లం ఎలా ఇస్తున్నారు, ప్లగ్ ఫ్లో ఇచ్చినాడా, ట్యూబ్లర్ రియాక్ట్ ఇచ్చినాడా, లేదా సిఎస్టీఆర్ ఇచ్చినాడా, వేరియబుల్ వాల్యూమ్ ఇచ్చినాడా, కాన్స్టిట్యుయెన్సీ వాల్యూమ్ ఇచ్చినాడా, వాల్యూమ్ కట్టమన్నాడా, టైం కట్టమన్నాడా, స్పేస్ టైం కట్టమన్నాడా, ఏం కట్టమన్నాడో క్లారిటీగా ప్రాబ్లం అర్థం చేసుకుని ఈక్వేషన్ ఒకసారి రికలెక్ట్ చేసుకుని గ్రాఫ్ గీసి ఏరియా కట్టి అక్కడ నుంచి వాల్యూమ్ కట్టామనుకోండి, మీకు ఈక్వేషన్స్ రికలెక్ట్ అవుతాయి. గ్రాఫ్ అటెంప్ట్ చేసినందుకు గ్రాఫ్ ఎలా కట్టాలో అర్థమవుతుంది. నేను ఊరికి ఇదన్నీ క్లాస్లో డిరైవ్ చేసుకుంటే దిస్ ఆల్ యూ కెన్ డూ దట్. చెప్తున్నారు కదా, ఈ మాత్రం చిన్న చేయలేరు మీరు. జీరో ఆర్ బదులు ఫస్ట్ ఆర్ డిరైవ్ చేయమంటే చేయలేరు. మైనస్ ఆర్ బదులు కేసీఏ 1 అని పెట్టి ఇంటిగ్రేట్ చేయలేరు. సిఏని మళ్ళీ సిఏ నాట్ ఇంటూ 1 మైనస్ ఎక్స్ వేసుకొని చేస్తే అది రాదు ఫైనల్ ఈక్వేషన్. సో ఇవన్నీ మీరు మేబీ ఏ పార్ట్ ఆఫ్ అసైన్మెంట్ మీరు చేయొచ్చు కదా. నేను అడగట్లేదు, నేను అడగను కూడా, ఎందుకంటే బికాస్ వీ హ్యావ్ లెస్ టైం. ఐ వాంట్ టు ఫోకస్ మోర్ ఆన్ ద ప్రాబ్లమ్స్. ఐ డోంట్ వాంట్ యూ డూ ఆన్ డెరివేషన్స్. బట్ ఎగ్జామ్లో డెరివేషన్స్ కూడా అడుగుతాడు, ప్రాబ్లమ్స్ అడగకపోతే డెరివేషన్స్ అడుగుతాడు. సో ఇవన్నీ మీ ప్యారలల్ ట్రాక్లో చేయాలి మీరు. ఓకే, లేదు అసైన్మెంట్ వెయిటేజ్ ఇమ్మంటే ఈ అన్ని డెరివేషన్స్ అసైన్మెంట్ ఇస్తాను, చేసుకోండి. క్లియర్? ఓకే. So fundamentally, batch reactor is unsteady state, whereas flow reactors, both flow reactors, CSTR and plug flow, are steady state reactors. Fine. Now, in both the reactors, for the flow reactors, you have tau into picture, but for the batch, T into picture. For the plug flow, there will be only lateral mixing. There will not be any axial mixing. But for CSTR, there is a back mixing, there is a overtaking, over mixing. So different names: back mix reactor, mixed reactor, continuous stirred tank reactor, continuous flow stirred tank reactor. Whereas for the plug flow, slug flow, piston flow. So unsteady state enti, steady state enti, batch enti, semi batch enti. మెటీరియల్ బ్యాలెన్స్ కంప్లీట్గా ఏముంటుంది, ఏ పార్ట్ జీరో అవుతుంది, అక్యుములేషన్ ఎందుకు జీరో అయింది, బ్యాచ్కి ఇన్ అవుట్ జీరో అవుతుంది, ఎందుకంటే బ్యాచ్ అంటేనే మీనింగ్ అది. అర్థమైందా? సిఎస్టీఆర్కి ప్లగ్ ఫ్లోకి పెర్ఫార్మెన్స్ ఈక్వేషన్ ఇంటిగ్రేషన్ ఒకటే మిస్ అవుతుంది. సో వి బై ఎఫ్ఏ నాట్ ఈజ్ ఈక్వల్ టు టౌ బై సిఏ నాట్ ఈజ్ ఈక్వల్ టు ఇంటిగ్రల్ ఎక్స్ఏ బై మైనస్ ఆర్ అంటే అది ప్లగ్ ఫ్లోకి. ఎప్పుడైతే ఇంటిగ్రేషన్ పడిందో గ్రాఫ్ షీట్లో ఓన్లీ పార్ట్ వరకు ఇంటిగ్రేషన్ తీసుకోవాలి, లిమిట్స్. ఈ ఫండమెంటల్ నాలెడ్జ్ ఉందనుకోండి, ఏ ప్రాబ్లమ్ అటెంప్ట్ చేసుకోండి. Okay, so we do some problems. So tomorrow I'll take a class and I'll keep it in the group which time it is feasible, because Kalyan sir is not there. I'm going to take the Kalyan sir classes, okay, according to my schedules. Okay, so bring the calculators, bring the graph sheets, and collect all the formulas. చాప్టర్ నెంబర్ 4 and 5 ఫ్రమ్ యువర్ లీవ్ అండ్ స్పిల్ టెక్స్ట్ బుక్. చాప్టర్ నెంబర్ 4 and 5 ఒకసారి చూసుకోండి. వీలైతే డెరివేషన్స్ చేయండి. ఈక్వేషన్స్ అన్ని టాలీ అవుతుందో చెక్ చేసుకోండి. రండి, వస్తే ప్రాబ్లమ్ సాల్వ్ చేయడం ఈజీ అవుతుంది. ఓకే.